Did you see it?
Okay, so first of all, I want to talk about the alternating series real quick, because that is the first time we talked about an error, right? So what was the alternating series error? The next term, okay? Hey, thank you. You just said it right there. Thank you. Okay. Now, when we are talking about a Taylor polynomial, terms are all, what do I want to say? The nth derivative over n factorial times x to the n. Do you agree? Okay, so when we talk about using a Taylor polynomial to approximate a function, it's also going to have some sort of error bound, just like when we talked about our alternating series approximating an infinite sum. Okay, so when we talk about the difference of our function and our polynomial, we have some remainder. And what's happening, our remainder looks like this. Okay, our remainder is no more than the n+1 derivative over n+1 factorial times x to the n+1. Now we have x minus c. C is just, well, what do you think C stands for?
Constant.
It actually stands for where our polynomial is centered at. Okay, so if we're centered at 0, C is 0. If we're centered at 2, C is 2. Okay, just like in your polynomial, it's like the A of what we talked about Friday. Oh, so Grace mentioned, isn't this basically the next term? Pretty much. Now, what is the one weird thing you see up there though?
Z.
Z. Z is not X. Okay, and I didn't make a typo. Okay.
Z is a constant.
Okay. So sometimes we might not be able to find the exact next derivative. Okay, so we're going to basically put a cap on it. This we're going to call the max of our derivative. Yeah, that f, the n+1 derivative of z. That z is basically saying we need to think about how big that derivative could be in the interval. Okay. So, yeah, it's here. Okay. We're also going to make sure that we think about this n+1 derivative on the interval. Okay, what do I mean by interval? Well, what we're going to do is we are going to use our Taylor polynomials to approximate. Okay, so like the first example that we're going to do, we're going to write, or we have a Taylor polynomial that is centered at 2, but we're going to use it to approximate x is 3. Okay, so how far off are we going to be? So when I say the interval, I'm talking about the interval from where are we centered to where are we approximating. Okay. Sometimes we're gonna have functions that automatically like give us an interval. Sometimes we're gonna have to think just a little bit. But just like the alternating series error, our Lagrange error bound is going to be the next unused term. We just have to think about our max n+1 derivative. Okay. What? Okay.
I like chew on my pencil when you guys like this. It tastes good.
All right, so let's go to example number 1. F is a function with 5 derivatives. We also know that the 5th derivative is less than 0.2. And the 4th degree polynomial for F is centered at 2 is used to approximate F of 3. Okay, so what's happening here? Okay, so let's say we have a 4th degree Taylor polynomial centered at 2. And we're using it to approximate F of 3. Okay, so in your homework, you wrote a bunch of really boring polynomials. Okay, what we're gonna do with those polynomials is we're gonna step away from the center and plug in a number. Now, is it going to be exactly what that function value is? No, but the closer we stay to the center, the more accurate we're gonna be in that approximation. Okay, didn't we decide that polynomials are way easier to plug into than any other function?
Yeah.
Okay. I want to know the error, or I want to know, which is basically the error. How accurate is the approximation? What's our error? Okay, so we want the remainder for when we plug in 3 to our 4th degree polynomial. Okay, well, that is going to be, since we're talking about a 4th degree polynomial, the 5th derivative of z, we'll talk about that here in a little bit, over 5 factorial since we're centered at 2, we have x minus 3. Okay, and so let's just, I'm gonna call this x for a moment, okay? In general, this is gonna be our error, okay? But since we're gonna plug in 3, I'm gonna replace this with 3 and this with 3. That's where 3 is gonna go. Hey, what's the biggest our 5th derivative is gonna be on this interval? What's 5 factorial? No.
120. No, 720. Wait, no, that's. Wait. What's 720 divided by 7?
120. So we have 2/10 divided by 120. You can use a calculator. Just help me out. .00167. Okay. So what we're saying is when we plug in 3 to our fourth degree polynomial centered at 2, we are going to be within 2/1000 of the actual f of 3 value. So I just went to 3 decimal places. Okay, so I'm gonna say this again. Okay, and right now we're just working with like a simple problem, although we don't get to see like everything happening. Like I get that. I have a function that I wrote a 4th degree Taylor polynomial for, centered at 2. I plugged 3 into that polynomial, and it's going to differ by the actual f of 3 by no more than 2/1000. Okay, so when I plugged in 3 to my 4th degree Taylor polynomial, it was 1.763. So let's find an interval that our answer would actually fit in. So this is the approximation from our polynomial. This is our error. So we are going to take our approximation and add 2/1000, and we're going to take our approximation and we're going to subtract 2/1000. So our actual function value of 3 is going to live in the interval 1.761 to 1.765. That's actually a pretty tight window. And we only use a 4th degree polynomial. What is this? This is the math symbol. It's kind of like a curved capital E. It means belongs to. Like it lives in that interval. Like the name of the symbol, I don't know. I just say belongs to. Okay, so could f of 3 equal 1.778? Okay, could f of 3 equal 1.764? Yes. I would not say it.
I say she.
Probably not any better.
She belongs.
Okay, we ready? Okay, what I'd like you to do is I'd like you to turn to the second page. And I would like you to do this and stop. Find the 5th degree Maclaurin polynomial for sine of x, and then stop. Oh, yeah, sorry. Sorry about the stop.
What? Naming it. I like how you
Okay,
write 5
4 and 5 do not get tick marks.
I like them. I thought 4 good.
No, 4 is 4.
No. I'm gonna get the big one. Have the prime part. What'd you think that she said, Josh?
Why?
I take a peek at this one?
First derivative.
Sure.
minus,
I don't think there's any. Are we gonna?
cosine of
Wait,
0.
what? It's gonna be 60 tomorrow. Is it gonna snow?
I have, they've taken it away. Again. No, better.
So-
What's up with first reward? Josh, what's up with Rusty?
Yeah.
Found it. Oh, do we have to write the polynomial?
Yes.
No, what? She likes that. She doesn't like
Andre, what's your polynomial? It's because he's not actually doing it. Andre, that's why he's not done yet. Dane, what's yours?
So it's on the derivatives,
I got you. You just have to.
30 seconds go.
Okay, 30 seconds.
How are you not allowed? Okay.
What do you got? Yeah.
Minus 1 over.
Are you taking
Wow.
x minus 1 over 3 factorial?
Yep. So yeah, if you write it like this instead, I have no problem with that. Might save some room. Okay. All right. Now use your polynomial to approximate sine of 1. Okay. So the sine of 1 is approximately our polynomial evaluated at 1. So what is 1 minus 1/6 plus 1/120th? Hey, we're no calculator. We're gonna do this.
120.
149. 100.
So we have 120 over 120 minus 20 over 120 plus 1. Okay.
You really find it.
Now we need to use Taylor's theorem to find the maximum error in our approximation. Okay, so I'm just going to talk about the error in general. We know it's going to be the So for a 5th degree polynomial, we're gonna look at the max of the 6th derivative. We're gonna look over 6 factorial, and remember, this is always x minus c factorial. Well, where are we centered at? Okay. Now, what did we plug in to our polynomial? We plugged in 1, so I'm going to plug in 1 right there. Okay. Now we need to think about what our max is on our 6th derivative. Well, let's come up here. What our 6th derivative be? Like the function. Negative sine of x. Okay. Well, let's think about what that looks like. What's the biggest y value that's going to happen on that graph? What about the smallest? Okay, so when we think about the absolute value of the max derivative, what's the biggest it's going to be? Okay. Now, you're not plug in 1 for z. This right here means figure out the maximum on that derivative. So we looked at our 6th derivative and we thought about where would the biggest be. And since it's the absolute value, sometimes you gotta think about the lowest, okay? So the highest we're gonna be is 1. If there was like an 8 in front of that sine of x, what would our max derivative be? 8. The amplitude is going to tell you that extreme, okay? We did. So we're talking about an interval. Okay. When you're dealing with a sine or cosine, all you have to do is think about the amplitude, because that's the biggest we're going to be. Like, we don't have to be like 100% exact on the interval. Okay. We're giving a cushion. Okay. Am I answering your question?
I just don't see.
You don't have to what?
Like, I don't see why you have to. Like, why you have to. It is.
That's what that means.
Yeah.
So we plugged
Yeah,
in
like-
1 for that.
I get like you're making like a cushion, so you like have more.
Okay. So let's come back to this right here. This is our next term. Now, when we were talking about our alternating series, we were just talking about, like, there weren't x's and n's. There were only n's in our alternating series. Do you see what I'm saying? Here there's x's and n's, okay? We're centered somewhere, but then we're plugging in a number further away. So we have this window of when we talk about our next derivative, is it bigger towards the center or towards the number that we're plugging in? So we have to figure out where that is to give ourselves the biggest cushion possible. Did that help?
Yes. But I don't understand what the center means. That's what they'll come on Friday. I took notes on the notes. I just don't want.
He took notes on the notes.
So what do we do next? So we just have to plug that in for the whole f to the n plus 1 z.
Okay, so do this. What is 1 divided by 720? Okay, you have a calculator in your hand, Andre. This is like the one time you could be helpful. What is 1 divided by 720? Zero, zero, one. Thank you. What is 101 over 120? 842. Okay, so we wrote a Taylor polynomial centered at 0. And then we stepped away from 0 and we plugged in 1 to our polynomial centered at 0. Now, if I actually plugged in 1 to our original function, the sine of x, we know that it would be between 0.842 plus our error and 0.842 minus our error. Now, yeah, I know you can plug in the sine of 1 to your calculator. Like, I understand that, okay? But also understand that that wasn't always an option back in the day, okay? And I wanted to give you a basic example to where you could wrap your head around it a little bit better.
Why is it like not like it's just the understanding the error, like how would it be closer or like you know what I mean?
So this is the max error. So the error could be smaller, but the error is not going to be any bigger than this. So the error could be smaller. So that's why we have like this range. Sine of 1 could be between 0.842 and 0.843. That should be a 1. But I'm basically giving you a 2 1,000th window that sine of 1 could be in.
Write down like the
Yeah, but what?
But like why is it I don't know. Later
You don't know your question,
yeah.
or you don't want to ask it?
No, I don't know. Like I'm
Okay. So can the sine of 1 equal 0.9?
no.
No, because it's not in that interval up there. Okay.
Are they really?
Okay, this is going to be really exciting. We're going to write the 4th degree Maclaurin polynomial for e to the x.
I know what it is.
I'll wait for you.
We have to write them all out right now.
I get the thing about this.
What's our first derivative? What's our second derivative? What's our third derivative? Okay, and what's e to the 0? Okay. So e to the x is approximately, we're going to write a 4th degree polynomial where e to the 0 is 1 plus our first derivative of 0 is 1 plus our second derivative is 1. Our third derivative is 1. Our fourth derivative is 1. And eventually you're going to remember that that's the path, but not today. So don't write this down, but we'll eventually write that e to the x is that's eventually what we'll get to.
I watched it with you yesterday and a bunch of times.
Okay, use your polynomial to approximate e. So E, what are we plugging in?
1.
Ooh, this is a no calculator.
Two.
39,
No.
17, plus 24, 41, 65.
65 24ths. Are you okay with y at 65 24ths?
Yeah.
24.
Answer on one of our quizzes.
What?
Is that an answer on one of our quizzes? The same problem. Yeah, well,
Sure. All right. So now let's talk about our error. The error for our 4th degree polynomial is max derivative, and that would be the 5th derivative over 5 factorial x minus, where are we centered at? 0. Okay, now we plugged in 1, so instead of x, I'm going to write 1. Okay, now let's think about our 5th derivative. What is our 5th derivative? I don't know what you're talking about. Rachel's saying things. All saying things. Okay. Our 5th derivative is e to the x. What's the maximum of e to the x? Oh, yeah, there is none because it's an increasing function. Okay. Well, let's think about our interval. Our interval is 0 to 1. Okay, but we're like not using a calculator, so I'm not going to throw in 2.7. Because that's an integer, since we don't have our calculator in the problem. Okay. I rounded up to 3. Okay. And so our error is 3 over 120. Which I'm going to, I mean, you don't have to, but what do you simplify it to? Actually, it's probably better not to simplify, because we are going to have to add it and subtract it to 65 24ths. You do what you want to. So e to the first belongs to the interval 65 24ths plus 3 over 120 and 65 24ths minus 3 over 120.
Yeah, I did.
You have to. What would you multiply 24 by to get our common denominator? Okay, what's 65 times 5?
The first.
Did you say 325? You would not need to simplify it. It's probably gonna more be like find this number and stop. But I'm trying to help you imagine what that number
It would
means.
be like E over 20. Or would we round to first?
I'm gonna go ahead for this non-calculator stuff, round to 3. But when you have a calculator, you can put E. All right. Example 4. Hey, calculator permitted. All right. And then I have a worksheet for you for homework. Okay. The function has derivatives of all orders of real number x. Assume that f of 2 is 6, f prime of 2 is 4, f double prime of 2 is -7, and f prime 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 of 2 is 8. That's how you say it, I'm sure. Write the third degree polynomial for f about x equals 2 and use it to approximate 2.3. So our third degree polynomial would be 6 plus 4 times x minus 2 minus 7 over 2 factorial x minus 2 to the second. I'm gonna mess that up. Plus 8 over 3 factorial x minus 2 to the third. I do not care if you leave it like this or rewrite it to be simpler, like 7 over 2 and 4 over 3 instead of 8 over 3 factorial. I don't care. All right, you do you. But what I want you to do, it's asking us to approximate f of 2.3. So f of 2.3 is approximately our polynomial when we plug in 2.3. Okay, here's what makes this nice. We're always going to be given a value close to our center. Okay, the further away you go, the less likely you are to be accurate. Okay, so we have 6 plus 4 times 0.3 minus 7/2 times 0.3 squared plus 4/3 times 0.3 cubed. Yeah, what is that number? Have a calculator.
I wrote down 7.
Did you give me something? What did your pod get? Okay, the fourth derivative satisfies the inequality. The fourth derivative of x is less than or equal to 9 on that interval. Well, that's nice, right? So our Lagrange error. We wrote a third degree polynomial, so we are going to worry about the fourth degree derivative over 4 factorial times x minus 2 to the fourth. Now, what number are we plugging in for x? What? It is 2.3. Okay. And what is our max derivative? 9. So our maximum error is going to be 0.003. Josh, I'll have you check me on that. Okay. So here was us approximating f of 2.3. This is going to be our maximum error. Could f of 2.3 equal 6.992? No, because f of 2.3 is going to live in the interval of 6.924 and 6.918.